Dear students, in this video tutorial, I will go through the process of modeling fatigue failure and predicting cycles to failure for a component using SolidWorks. The example that I've chosen is from the book Analysis of Machine Elements using SolidWorks Simulation, and it's the 16th edition of this book from Nadehi and Stefan. So we'll be following this example, and in this example, we have got a cantilevered beam. So this is completely fixed from one end, and on the other end, which is the free end, we have a 1500 Newton cyclic fully reversed load being applied. So this is one of those situations where we have got the full reverse of the load. So that means the mean stress in this case is 0. And in the length of this rod is 250 mm. It has a circular cross section with 25 millimeter diameter. We have defined a point of interest at 50 mm away from the origin, which is from where the rod is fixed. You can have other points of interest as well, especially when you do your assignment. You'll find that you'll actually have each group will have a different point of interest. And in addition, I will also have a horizontal force in that case. But first, let's focus on this problem, and then later you can discuss with me in the class if to see what will be the differences in the assignment that you do. For this rod, the material is AISI 1020 steel, and I will also show you during this simulation that how we can predict the SN curve for this material and how we can input that into SolidWorks. So let's now start SolidWorks and start with our simulation. Okay, now for this particular model, I have already created the part file, downloaded the part file, which I will open now. So, or you can actually start it from the scratch and just simply define the part file itself. Let me quickly do this as well because some of the students are not very familiar with the basic operations of SolidWorks. So for them, I will create the part file as well. However, for your ease, I have already uploaded it on D2L. So I've select the right plane so that my bar can be extruded in a way which is consistent with the definition in the book that it's basically in the length is along the x-axis. So with that plane selected, I will now sketch my circle that is going to be basically of the required diameter. Now I forgot to change the units, so I can change them now to millimeters. Okay, and therefore I'll have to go back to my sketch, edit it again, and this time when I click on this, I will be able to give the required value of the diameter. So this was because it is 25 millimeter diameter, so the radius is going to be 12.5. So with the 12.5 millimeter of the radius, now we have got our part basic sketch defined. If you want, you can add a dimension just to be sure that you know this is the correct one. So yes, you've got 25 mm diameter over here. Now I will exit the sketch and then I will go into the features and I will select this sketch and I will extrude. And now it is going to be extruded along the X direction with a length of 250 millimeters. So with that extruded, now we have our basic part defined. Now, so I will call this as my fatigue cylinder, and I'll do this for section 5. With this one, I will then also create I can always create the split line for the point of interest later on in the post-processing, or I can just simply do it now. So to do it now, what I will need to do, I will first need to create a reference plane. So reference plane. So at the required distance. So I will create the plane and I will make this plane parallel to my right plane. and I will have it offset from the origin by the given distance. Now, for me, this distance is 50 mm. For your case, it can be different depending on the one requirement in your assignment. So right now, this is my, so I'll call it as 50 mm ref, just for so that I remember if I have multiple. And now, once I have this, I can now create a split line, and this split line will allow me to then later on look into the results at this. So I've selected the main plane, and then I will also select the face which has to be cut. So you can see here, so it's a natural split, and I'll just say OK. And in this case, now you've got two zones. So basically, later on, you can use this edge to calculate the life at that particular edge. So this part definition is now complete. So maybe it's a good time to just save the model as well. So I will create it as I will call this part as fatigue cylinder section 5. So that is different from the one that I already have in the folder. Okay. So once I've saved it, I can now proceed to setting up the analysis. Now, one thing that you need to keep in mind is that when we are going to set up a fatigue analysis, it always starts by first carrying out a linear elastic stress analysis, and then the results are basically carried forward into the fatigue study, in which then the life is predicted. So I will first do the first part of setting up my linear elastic analysis. So I'll go into the simulation tab. I'll select on new study, and now I can give it any name that I prefer. So I will call this one as um, static cylinder bending. So I'll call it as static cylinder bend. This is a static study, so this is already selected. And then I will basically just select on uh, okay, oh, sorry, I think I just clicked it again, so that's why it deleted the name. Okay, now my initial study is being set up. I can start by assigning the material. I'll go into apply edit material, and in this case, as I described in the start, the material is AISI 1020 steel. So I go for ASI 1020 steel, and I'll keep the units right now in megapascals. Later, if I have to change the units to pascals, I can also do that. So for now, I'll keep the units as in pascals. So with that, material has been assigned, and I'll just say apply, and I'll say close. So my material properties have been assigned. Next step, as always, is to assign the boundary conditions. Now, when I assign the boundary conditions, because one of the ends is completely fixed, so I'll go for fixed geometry. And in this case, I will choose this end. So I'll basically select this face as well as the required edge. So I'll click on both of them, and then I'll say OK by clicking the green arrow. And now I've basically fixed my edge. The next step is to apply the external load, which in this case is a 1500 Newton force. So I will apply that on the face, which is free. So I'll right click on this, go for force, and in the force, I will select the units as SI, they're already there. I'll enter the amount as 1500 newtons, and I will now select the face. But if you just click on the face right now, what you're seeing is that the force is acting as if it is in acting into the cylinder. But this is not what we want. We want it as a bending force. So what I need to do is I need to select uh, the particular direction in which I want to apply this. So to give it the direction, I need to define, I basically need to select a surface which will define the direction. So for reference, I'll just use the back face for the direction. And then based on this, I can actually assign it along the plane direction one option, and there I will enter the value of the load. So right now, if you look into this, so this is along the plane direction one. Okay, now this is being applied in upward direction. In reality, it does not really matter whether this is being applied upward or downward because of the nature of the fatigue loading. It has to be cyclic. But to keep it consistent with the book, I will just choose reverse direction over here and enter the magnitude of 1500 newtons. Later on, when we carry out the fatigue analysis, this load will be reversed as well. So with that, I'll just say okay, and then basically I have now defined my both fixtures as well as external loads, and I've also assigned my material. So the next stage is to carry out the static analysis, like we always do. So in this particular case, for the static analysis, I'll need to define a mesh. So I'll go and I'll say create mesh. Now, for fatigue studies, I always recommend using a high quality mesh, and I also recommend using a fine setting for the mesh because it's highly sensitive to minor changes in the mesh because the results will, because of the log nature of the fatigue life plot, stress and life plot. Even small changes in stress can lead to quite large changes in the life prediction. Therefore, it's better to use a fine mesh. We'll use the standard meshing technique for now, and I will just mesh it using a high quality mesh. So I'll now click on the green arrow of OK, and now you can see we have got a reasonably fine mesh over here. Now with this mesh defined, I can actually run the study. Now, in this case, I'm not basically going very much interested in any specific variables other than the von Mises stress and the overall displacement. So I will run the analysis and I will basically look into the values of those. So you can see here, this is around 235 megapascals is the peak stress around here. Yeah. If you want, you can click on Edit Definition to basically view the results in megapascals. And if you view it in true scale, you'll be able to see this as it is. And you can also show the maximum value. So I'll do that and choose a floating representation. So now you can see here that your maximum rod is behaving like a cantilever with a maximum of around 234 megapascal of stress. If you want, you can very quickly validate this number as well by carrying out a simple analysis using your beam equation, mc over I. And you should get a number which is close to this number for the normal stress. Because the cylinder is fairly long, the contribution of the shear stress will be small. Although this is von Mises stress, so your number of the normal stress will not exactly match this. Rather, you'll have to put it in the formula for von Mises stress to get the correct value. Okay, but I'll not do the hand calculations right now. Rather, I'll wait until the end of the video when I will actually then show you and take you through the process of the hand calculations to verify the model. So the displacement you can also see here is around 2.04 mm, and this value of displacement can also be validated using the formula of the deflection of a cantilevered beam, and you can also quickly check this to get a quick sense on whether the numbers are correct or not. However, I can verify that this is the expected value. Right. Now, once we have the static test done, it's time for us to move to the fatigue analysis. And I will pause the video at this stage, and I think I will do is I will split the video into two parts. So for the fatigue part, I will then record the video in a separate file.